Hello again. Welcome. Today we will talk about the simplex method, which was developed in 1947 by Dr. George Dantzig. Before we talk about the simplex method, I would like to make a few reflections about the linear programming problem based on the graphical method. For instance, imagine the following problem. If you plot the equations, you will surely obtain the following graph. Taking into account the non-negativity constraints, we have a set of 5 constraints. Now, I ask you to observe the vertices of the feasible region. As you can see, these vertices always correspond to the intersection of 2 of the equations which are part of the constraints set. Besides these vertices, there are also some other vertices which were not considered because they do not satisfy all the constraints. In reality, given that there are 5 constraints, and that we must solve systems of equations with 2 variables, then the number of systems of equations that we must solve is a combination of 5 elements taken 2 at a time, which will result in a total of 10 systems of equations. If you observe the figure, you will realize that there are 9 vertices. This happens because the lines, x1 equal to 8, and x1 equal to 0, represent parallel lines, and hence, the system of equations does not have a solution. Without the simplex method, this reasoning might be the only one we could use to solve a linear programming problem. For instance, now imagine the following problem. In this case we will have 7 equations, and given that we have 4 variables, then a way to solve the problem may be to solve 35 systems of 4 equations with 4 variables. And after obtaining these 35 points, we must verify which of them satisfy the other remaining constraints. As you can see, this would mean a long process. Fortunately for us, the simplex method is available. Let me explain how this method works. To do this, let us go back to the original problem. And even though we will consider the non-negativity constraints, we will not explicitly write them. In this problem, we will let z be the objective function value. The key to apply the simplex method is to transform these inequalities into equalities. This is done adding new variables to the original problem. The variables that were added are called slack variables, and they must also satisfy the non-negativity constraint. That is, these variables are also greater than or equal to 0. For instance, think about the first constraint. If the value of s1 is greater than 0, then the value of 2x1 plus x2 will be smaller than 20. And if the value of s1 is 0, then the value of 2x1 plus x2 will be equal to 20. In this way, the constraint 2x1 plus x2 less than or equal to 20 is satisfied. The same applies to the second and third constraints. Now we have arrived to a system of 3 equations with 5 unknowns. Given that we have more variables than equations, it is possible to set some of the variables equal to 0. Given the problem structure, an easy way to find a solution is to set x1 and x2 equal to 0, and then, the system is reduced to the following system. It is obvious that this represents a solution to the system of equations. But this solution makes the value of z equal to 0, and we are interested in maximizing this value. If we observe the expression which represents z, then we can see that the value of z will increase faster if we increase the value of x1. Now, we must ask ourselves up to what value we can increase x1. To answer this question, we must observe our constraints. In the first equation, given that the value of x2 is 0, then the equation can be written as follows. And since the smallest value that s1 can have is 0, then the largest value that x1 can take is 10. Similarly, we analyze the second constraint. In this case, we can see that x1 can increase up to 18 units. In the third constraint, x1 can increase up to 8 units. Therefore, the constraint that limits the most the increase of x1 is the third constraint. In this constraint, we solve for x1. We will use this expression to substitute the value of x1 in the objective function, as well as in the other constraints. Substituting in the objective function, we obtain the following expression. Now we simplify and arrange these variables. And hence, z is equal to 56 plus 4x2 minus 7s3. Now we substitute the value of x1 in the first constraint. Now we develop the expression. By simplifying and arranging again, we conclude that the first constraint can be expressed as x2 plus s1 minus 2s3 equal to 4. Now, we substitute the value of x1 in the second constraint. Now we arrange and simplify. To get the expression, x2 plus s2 minus s3 equal to 10. We should not substitute the value of x1 in the third constraint, since from this expression we solve for x1. On the other hand, we will substitute these equations in the objective function and in the first and second constraint respectively, and we will arrive to the following expressions. Even though the expressions are different, this system of equations is totally equivalent to the previous one. As we did before, we will set some variables equal to 0, which in this case will be x2 and s3. And we will quickly arrive to the solution. An easy way to identify the variables which will be set to 0, is to visualize which of the variables appear in the objective function. Another different way, is to identify the variables which won't be 0. These variables are called basic variables, and appear in only one of the equations, with coefficient 1. On the other hand, we can deduce that the value of z will increase if the value of x2 increases, and z will decrease if s3 increases. Since we are maximizing z, we are interested in increasing its value. And therefore, we will try to increase the value of x2. Since s3 is equal to 0, then x1 plus s1 is equal to 4. And since the smallest value of s1 is 0, this means that x2 must be less than or equal to 4. Similarly, in the second constraint we can deduce that x2 must be less than or equal to 10. In the third constraint, given that s3 is equal to 0, then, x1 is equal to 8. Since x2 does not exist in the expression, then x2 can increase without limit. The constraint that limits the most the increase of x2, is the first one. From that constraint we will solve for x2. Observe that the objective of this step, is to determine the constraint from which to solve for the variable whose value we wish to increase. Solving for x2 in the first expression, we obtain x2 equal to 4, minus s1, plus 2s3. We must substitute this value in the objective function. Now, we develop the expression and simplify. By doing this, we arrive to z equal to 72 minus 4s1 plus s3. We won't substitute the value of x2 in the first constraint, since this is the constraint we use to solve for x2. Now we will substitute the value of x2 in the second constraint. Simplifying the expression, we must obtain the following. In the third constraint we cannot substitute the value of x2, since this variable does not exist in this equation. Summarizing our findings, only the objective function and the second constraint will change. With these expressions, we build a new system. Now set S1 and S3 equal to 0. When we do this, then, x2 is equal to 4, s2 is equal to 6, and x1 is equal to 8. We must also note that, z is equal to 72, minus 4s1, plus s3. This means that, if we increase the value of s3, then the value of z will increase. As in the previous occasions, we must determine which of the constraints limits most the increase of s3. Given that, s1 is 0, then the first constraint is, x2, minus 2s3, equal to 4. This expression is very interesting, since the coefficient of s3 is negative. This means that if s3 increases, then the value of x2 also increases. For instance, if s2 increases its value to 10, then x2 increases its value to 24 to preserve the equality. This means that s3 can increase its value with no limit. That is, the first constraint does not limit the increase of the variable s3. Notice the difference with the second constraint. In this constraint, the coefficient of s3 is positive, and if we think to increase its value to 10, then s2 will take on a negative value. Which is not possible, because the non-negativity constraints. In this case, s3 must be less than or equal to 6. In the third constraint, s3 must be less than or equal to 8. Therefore, we will solve for s3 in the second constraint. This value will be substituted in the objective function and in the first and third constraints. And now we have the following system. If you observe the system, you will realize that s1 and s2 will be assigned a 0 value, and x2 will be equal to 16, s3 equal to 6, and x1 equal to 2. But something more important is the following: the value of z is equal to 78, minus 3s1, minus s2. This is very important since if we increase the value of s1 or the value of s2, then z will decrease. That is, z has reached its maximum value. This maximum is reached at the point 2,16, and the maximum value of z is 78. If you observe the computations we have made, you will realize that in the first iteration the value of x1 was 0, the value of x2 was 0, and the value of z was also 0. In the second iteration, x1 is equal to 8, x2 is equal to 0, and z is equal to 56. In the third iteration, x1 is equal to 8, x2 is equal to 4, and z is equal to 72. In the last iteration, x1 is 2, x2 is 16, and z is equal to 78. Let us keep these points, and go back to the graphical method. If you observe the vertices of the figure, you will realize that the solution started at the origin, then it moved to the point 8, 0, then to the point 8, 4, and finally, to the point 2, 16. This is the mechanics of the simplex method. The method travels from one vertex to another adjacent vertex, which improves the solution. When none of the adjacent vertices improves the solution, we have reached the optimal point. I believe this was a long explanation, but I hope it was worth it.
See you soon.